My final year project is author classification through data mining. It aims to enable classification using various data mining techniques and investigate performance. It's one possible application of big data and uses standard and cutting-edge tools such as Python and TensorFlow. The data is gathered from Twitter from two different accounts, Real Donald Trump and Hillary Clinton. These are my two authors. The data is gathered through a Python script and a Twitter developer API. Tweets are gathered up to 140 characters long over the same end of election period time. The tweets are pre-processed to avoid a rubbish in, rubbish out situation. Therefore, significant time was invested to avoid misleading results due to bad data. Preserving formatting and special characters was important, as was using a stop list to remove noise words which don't contribute to the meaning of a tweet. From this, a vocabulary was built and feature vectors were able to be obtained. Feature vectors aim to represent the data statistically and extract characteristics of the text. My feature vectors were called bag of words vectors, as they used a multi-set of words to represent each document. I used two different methods for this: term frequency, which just counts the number of times that term appears in the document, and term frequency inverse document frequency, which multiplies this term frequency by a weight, which aims the IDF weight, which aims to de-emphasize words which appear a lot in many documents. Vectors were also normalized to remove the effect of document length on the vectors. One of the main problems I ran into was dimensionality. Using term frequency, we get about 12,500 features, and using term frequency inverse document frequency, we get about 8,000. This gives us a data matrix of over 80 million dimensions, something that's far too big. We then reduce this using something called singular value decomposition, which takes us down from 8,000 features to about 50. SVD works for computing a data matrix M, U, sigma, and V transposed. This can then help us reduce dimensions by finding the largest singular values and associated dimensions and discarding the rest. The singular values can be found in the diagonals of sigma, and the corresponding columns of V are our new basis vectors. This gives us a new matrix M prime, which is an approximation of M, using a reduced U, sigma, and V. If we want the eigenvalues, such as we get through PCA, we can compute a covariance matrix, M transposed M, and this shows us that the singular values are simply just the diagonals of sigma squared. This is actually now the industry standard way of computing eigenvalues, due to its sidestepping PCA and some of its associated issues through precision. Classifiers are a way of sorting these feature vectors into one of two authors. The diagram on the right shows how a classifier works, taking three different inputs and outputting the most likely author. I implemented 7 different methods, including 4 vector space methods, such as cosine similarity, which finds the angle between a new document and the author's vectors, as well as k-nearest neighbour, which is a standard classifier, and a support vector machine, which aims to discriminate between the two authors. Furthermore, a classification tree method in the form of a random forest was used, which again is a majority vote using randomly generated decision trees. However, the thing that piqued my interest most was a neural network, and so I'm going to talk about that a bit more. A neural network is as shown here. This is what we call a graph. As you can see, its structure is made up of multiple layers. Each layer has neurons and nodes, and the number of neurons or nodes are determined by different factors. For example, input vector features determine the number of input layer nodes, and the number of classes determine the number of nodes in the output layer. If a network has hidden layers, like the ones shown here, it's called a multi-layer perceptron. However, if it does not, like a logistic regression network, the input is connected directly to the output. The number of nodes in the hidden layer is up to the programmer's discretion. In my case, I used 25 for various reasons I'll discuss later. I've implemented one neural network using multi-layer perceptron, and one neural network using logistic regression. The most important characteristic of a neural network is the weight of each node. This determines how the node reacts based on inputs. This is adjusted through something called error backpropagation during training. As the code is written myself, and I built the tools myself, many of the parameters have to be adjusted manually. Some of them are adjusted automatically through the use of functions, such as error backpropagation of the weights. However, others, such as the number of nearest neighbours and KNN, or the SVM kernel functions, are up to me. The optimal parameters were found by varying them one at a time, or consulting relevant literature, such as the number of nodes in the hidden layer being recommended to be between the input and output layers for a good mix of accuracy as well as reducing the risk of overfitting for the data. The results are generated using these optimized classifiers and feature vectors. I ran each combination 20 times to try and remove the effect of random initialization from the results. I used 6,500 training vectors and 2,150 test vectors. I ran over 7 different classifiers using 7 different types of feature vector. This graph shows all of my results. It's interesting to note that the bottom 6 classifiers are non-dimension reduced data. This tells us that non-dimension reduced vectors are very noisy, and therefore performance is unpredictable. As you can see, they're below chance, 50%. The top combination of a logistic regression and a dimension reduced vector gave greater than 88% performance. Taking a closer look at the top 10 classifiers, we can see that the top 2 are neural networks. However, the top 10, there's only 6% variation between the first and the 10th. The question is then, is something like this more significant than something like this? Or is it just run-to-run variation and margin of error? To solve this, we can use something called statistical significance. The central limit theorem tells us that for a large number of runs, the distribution of this is Gaussian. Therefore, we can say that 95% of the variance lies within 2 standard deviations, giving us a range where the accuracy is statistically indistinguishable. Applying this to our results and taking our top combination as significant, we can see that only combinations 4, 9, 12, etc. are actually significant and statistically discriminatory compared to the other combinations. Furthermore, we can see that the 2 methods to classify authors using discriminatory classifiers show better performance than non-discriminatory classifiers. Throughout the project, I implemented various things. Apart from the system to run optimal combinations on a large corpora to generate the results you just saw, using multi-threaded programs and GPU compute, I've also written a graphical user interface, which allows for manual input and testing, as well as demos. Furthermore, I have a working Twitter bot, which automatically classifies tweets tweeted at it. This has had over 90 public uses so far. The insights I've gained over this project have been numerous. I can say that there's an observable difference between the 2 authors, which I've been able to expose to over 88% accuracy. We can say that the data is most likely linearly separable, as we can see that there's no significant difference between the multi-layer perceptron and the logistic regression. This shows us that more layers are not effective in increasing accuracy. We can also say that the classifier has a bigger effect in the feature vector. Despite using very simple feature vectors, we were able to observe good performance. This is actually surprising, as the 2 authors are talking about very similar topics with just different slants on them. Furthermore, dimension reduction played a big role in this, due to the noisiness of the data, improving both accuracy and speed. This shows the prowess of neural networks and data mining as a whole, and it's why it's such an exciting field. Thank you very much for listening.